Hello everyone. So today we have a question regarding using Bayes' theorem. So we gonna use Bayes' theorem to find like the posterior distribution of P if we have given some data. So in general, so let's start with, suppose we have given the data x given P. This is follow binomial distribution with n number of trials, and P is the probability of success. So we can write f of x, P is combination x out of n, P to the power x, 1 minus P to the power n minus x. And we know that x take values 0, 1 up to n. Now suppose also we have the prior density here. So this is prior density of P. Can write it as pi of P. Before we should, for example, say so it's P follow beta distribution with alpha equal 2 and beta equal 1. So you can say pi of P, which is the prior density, is equal to 1 divided by beta function of 2 and 1, and then P to the power 2 minus 1, 1 minus P to the power 1 minus 1. So basically this is the function beta 2, 1. So the answer for this function is half when you so there would be 2 because the half in the denominator, and then would be 2 in the numerator. Now, and this one will be P, and that will be equal 1. So the function is the prior density is 2P, where P is between 0 and 1. Now we know from we have the posterior density, or the posterior is proportional to prior times likelihood. So the likelihood is binomial, and the prior here beta. So we just need to so we define the posterior as like probability of P given we observed the data x. So that will be proportional to pi of P times L of P given x, or we can so the prior here I've got 2P, and then we can write so let So we can write that that's P, because the 2 is just go with the proportionality sign, and then we have P to the power x minus 1 minus P sorry, it's P to the x 1 minus P n to the power n minus x. Now we can see this one, we can just say write this down, so that will be P to the x plus 1, because they have the same the same base here, which is P, so it will be P to the power x plus 1 minus P n minus x. We can notice that this function here, this distribution, is the kernel density of a beta distribution. So we can write that. So we can write the kernel density. So it's pi of p given x is p to the we have x plus 1, and then 1 minus p to the power n minus x. We can write this as p to the x plus 1, oh sorry, x plus 2 minus 1, so that will give me back x plus 1, and then 1 minus p to the n minus x plus 1, and then minus 1. So this is in the exponent. This one is, now it's, this one is called alpha star, and this one is beta star. So we can write the full distribution of P, posterior density, or the posterior density, as follows. So that will be 1 divided by beta function of x plus 1, sorry, x plus 2, so it's x plus 2 and n minus x plus 1, and then p to the power x plus 2 minus 1 minus p to the n minus x plus 1 minus 1. Now p is between 0 and 1. Now from this posterior density, now we can find the posterior mean and variance as follows. Because p given x, posterior here, is beta with x plus 2 and then n minus x plus 1. So this is alpha star and this is beta star. Now we know that expectation of p given x, that will be from the definition of expectation of beta distribution, that will be alpha star divided by alpha star plus beta star, which is equal to x plus 2 and then x plus 2 plus n minus x plus 1. So minus x cancel out with x. So that will be x plus 2 divided by n plus 3. So that will be the expectation of p given x. This is posterior mean. This is called posterior mean of p. Now, suppose we have observed x equals 7 and then n equals 10. So the posterior mean of p equal to, we said x plus 2 and then n plus 3. So that gives me 9 divided by 13, which is equal 0.692. So this is the posterior mean. Now we can find also the posterior variance of p given x, which is equal to x plus 2 times n minus x plus 1 and then n plus 3 squared times n plus 3 plus 1. So that is give me 36 in the numerator, and that give me in the denominator is 13 squared times 14, which is it give me the variance is 0.015. So this is the variance of the posterior variance, and this is the posterior mean. We can do now the comparison between the posterior mean, posterior variance with the prior mean and prior variance. So now we can find the prior mean as E of p, which is, as we know, it's the integral from 0 to 1 p f of p, or what we call a pi of p. So that would be 0 to 1 p times 2p dp. And so that will be 2 integral 0 to 1 p squared dp, which is equal to that, which is equal to 0.666. And then the variance of p is equal to, because we have alpha equal 2 and beta equal 1. So the variance will be 2 times 1 and then 2 plus 1 squared, then 2 plus 1 plus 1. So that equal 2 divided by 9 times 4, which is 2 divided by 36, which is 1/18, which is equal 0.05 5. This is the posterior mean. Sorry, this is um, the prior, sorry, this prior variance, and this is the prior mean, this one. So we can write that, for example, in a table. So let's say this is the prior in summary. So this is a prior, this is the posterior. So this is the A mean expectation, and then the V is the variance here. So the prior mean is 0.666, and the prior posterior mean is 0.692, and the prior variance is 0.055, and the posterior variance is 0.015. We can see this variance for the posterior variance is small than the prior variance. So that means there is more uncertainty about the inference about P when we have observed some data. I hope you enjoy this video, and thanks for watching.